Hello again and welcome. In this video I'd like to demonstrate some of the new features that I've added to my software for the NanoVNA. That software is available on GitHub at no cost. I'll provide a link to it in the description. You may remember this circuit board from my review for the NanoVNA Plus. This is just a couple of patch antennas. Again, these were tuned for 2.3 gigahertz. One of the features I thought I would demonstrate with these was how radar works. You can see I have another piece of circuit board material. I'm just going to lay this next to our two patch antennas. This is looking at the new software. You can see it's located the NanoVNA V2 Plus 4. So if we set our center frequency for 2.35 gigahertz and the span of 100 megahertz, this is what it looks like. Now the first versions of the software that I released, the transmission polar function actually displayed S11 as a Smith chart. So that function had never worked. I left it in there as a placeholder, assuming that at one point I would actually implement it. So let's just go ahead and we'll select it. You can see we have this circle around the center. And what I'm going to do now is select reference, and then I'm going to select channel N minus the ref. So this is going to make a relative measurement. And you can see it moves our cursor off to the far right. Another thing that's changed with this software, originally all of the cursor measurements couldn't handle a relative measurement. That's been changed on this new release, so no matter what you're actually measuring, if you've enabled this relative measurement by selecting the CHN minus ref, that's going to be reflected in all of the readouts. Let's see what happens now as we move our circuit board away. Notice how our curve is rotating clockwise around the axis. And it's also getting closer to the center as we move it farther away. Again, what's happening is we are transmitting a signal off of port 1. It's being fed to this patch antenna on the left. It's radiating and it's bouncing off of our piece of copper here, and it's feeding back to our other patch antenna, which is set on port 2. So we're looking at the transmission between the two. Watch what happens as I place my hand between the two antennas. You can see how the arc moves towards the center. It has the same effect as us moving the copper away. As a matter of fact, let's just go ahead and remove it. And again, as we start getting closer to the other antenna, you can see we go back to the 0 point. And you can see as I push this even closer, how the arc moves beyond the 0 point. Let's just go ahead and we'll store this as a new reference. Again, it brings it back to the 0 point. Here we have a piece of paper. Let's just stick that between our two plates. And you can see that has no effect. Here we have a anti-static bag. And let's lay that between the two. And you can see now how that interferes with the transmission. So again, just a real simple demonstration of how you can utilize this polar display. Next, what I'd like to display is measuring the capacitors Esr. And you can see in the upper right corner of the cursors, we now have an Esr readout. This is just a 82 nanohenry in parallel with a 32 picofarad capacitor. This has a resonance of 98 megahertz. Let's just go ahead and we'll attach that to our NanoVNA. So first thing we're going to have to do is calibrate the unit. We'll turn off the channel reference. We can select port 2 cal. We'll select old calibration, and we'll just select this 1 to 100 megahertz one port SOLT cal. So we don't have anything connected right now. You can see our trace is rotating counterclockwise around the 0 point. As we attach our open, you can see we have our dot off at the 0 point on the right. So again, let's just attach our little circuit, and we'll notice that we have this semicircle, and if we place the cursor on the point where it crosses the 0 point, and you can see our frequency at that point is roughly 95 megahertz. Let's just bring our B cursor to the other side of that. It looks like there's only one data point where cursor A is at 95.2, cursor B is now at 96.7 megahertz. So fairly close to 97 megahertz. Again, we had calculated 98 megahertz for this. So the point with this is that Again, looking at the Smith chart, is we're in this area down here, we're looking at capacitive reactance, and up here we're looking at the inductive reactance of this circuit. And the point I want to make again is that the resonant point is where X sub C equals X sub L. So if we look at a simple model for a capacitor, it's going to have some inductance, some series resistance, and of course a capacitive element to it. And the series resistance is called the equivalent series resistance, or ESR, and this is what we're interested in looking at. So one way to make that measurement is to place our device between port 1 and port 2, but instead of placing it in series, we're going to place it in parallel. So this is called a shunt through measurement. So you can imagine if our load here happens to be a capacitor, this capacitor is going to have a resonant point. So if we're plotting the transmission, it's going to look something like this, and this dip is going to happen at the resonance. And again, remember what we said, that X sub C is equal to X sub L at the resonant point. So when we're looking at this dip, X sub C and X sub L are equal, so they cancel each other out, and what we're left with is just the ESR. So here I have a couple of capacitors. The one on the right, this is just an aluminum electrolytic, and of course this is a ceramic disc capacitor. So here we have one of my RLC meters. Let's just go ahead and insert our capacitor. You can see it's 2 nanofarads essentially, and it's running currently at 1 kilohertz. And you can see we can measure the D as well as the Q. But you'll notice this meter also has ESR. The way that you would use that, you have to take it out of parallel mode. So we go to series mode, and now we can select ESR. And you'll notice this shows an ESR of 350 ohms for that ceramic capacitor. So here we have a, I think, 4.7 ohm resistor. Let's just go ahead and insert that. And sure enough, you can see it reads roughly 4.622 ohms. So fairly close. You might think that, wow, you know, is that capacitor really 320 ohms? Of course it isn't. It's a ceramic. It's going to be less than an ohm. Well, if you take the time to read the manual for this particular meter, they'll tell you that if you want to measure ceramic capacitors, or essentially values that are lower than, I think, 1 microfarad, basically you want to run this thing in the parallel mode. So essentially what they're telling you is ESR isn't valid for anything below 1 microfarad. Of course, if you're working at higher frequencies, you're probably not using aluminum electrolytics. You're probably using the ceramic capacitors. So what I'd like to demonstrate is measuring this same capacitor, and we're going to use the Nano to do it. So the first thing we want to do is select transmission. Again, if we go to Setup Diagnostics, this is where the model is selected, and you can see I have this set for the custom ideal standards. Again, I've always just used the ideal model with these standards. So let's go ahead and we'll attach the through. Right, with our software, you can see we are currently not calibrated. Let's go ahead and change our stop frequency to 400 megahertz. And let's select transmission rectangular. And we'll store this as our reference. And we'll select our channel N minus reference. And you can see we're displaying roughly 0 dB. Let's go ahead and remove the open. And you can see we're down at around 90 dB or so. So here I have a small fixture that I've built. You've probably seen this in other videos. I've used this to look at through-hole components. Let's just go ahead and attach that between our 2 ports. You can see even with our through jumper, it's added some air. It's down roughly 0.06 dB. Let's just go ahead and attach our aluminum electrolytic. Again, this is our ground on the 2 sides of the Nano, and the capacitor is sitting right between these 2. And we can see there's this definite dip down here, and we are calculating with this capacitor roughly 2.8 or so ohms of ESR. Now, to be clear, there's some problems when you make measurements like this. First of all, you'll notice that there's this ground loop between these 2 connectors. Normally what you're going to do is you're going to place some kind of a common mode choke between these two ports. And the whole idea of that is to break this ground loop. Normally when I'm trying to make low frequency measurements like that, I have a different piece of coax. This is just loaded up with ferrite. And the whole idea of this is to make this braid lossy. Now again, we're working at frequencies where the cable itself is going to become quite lossy, so this isn't really going to pose a problem for this demonstration, so we don't have a need to really load this thing up. The other problem with making this measurement is, of course, there's quite a bit of port mismatch here. What you may find that you need to do to improve the return loss is add an attenuator to this side. You may actually have to do it to both sides to get a decent measurement. Again, it's going to depend on the range of the parts that you're trying to look at. You just have to experiment with it. So let's have a look at our other ceramic capacitor. Now again, the resonant frequency for this part is going to be much higher than this electrolytic. So let's go ahead and we'll save this to memory 1. And let's have a look at our ceramic capacitor. Again, this is going to have a much higher resonant frequency than our aluminum electrolytic. And we can see now it has a dip that goes down quite a bit further. It's like minus 33 dB, and we can see that it's moved over to the right slightly. The frequency on this now is roughly 15 megahertz. You can see we're calculating an ESR of roughly 560 milliohms or so. Part of the problem with using a fixture like this and having these long leads is, of course, this will add a fair bit of error to the measurement. So normally what you're going to do is you're going to take whatever part you're trying to model, you're going to cut these way down. You probably are not going to be using a socketed fixture like this. I would normally just solder whatever I want to test right down to the circuit board and then take the measurement. So I would expect that the ESR for this part is going to be a fair bit lower than what we're measuring with the Nano. So what if we wanted to look at a more typical RF capacitor? These were made by American Technical Ceramics. These are a 100B series, just a jelly bean RF component. At 150 megahertz, these have a Q of 150, and they have an ESR of 20 milliohms. This is looking at their software. Let's just go ahead and select 330 picofarads. And again, we're using the 100B, so this is the part that we want to look at. And again, you can see it has an ESR of roughly 22 milliohms. Let's go ahead and we'll select the part data sheet. And now you can see we're presented with this graph. We can display Q versus frequency. Let's go ahead and look at the ESR versus frequency. So we can see below 20 megahertz or so, the ESR is below 10 milliohms. As we get up around 200 megahertz, we're getting close to about 25 milliohms. And at 300 megahertz, we're at about 30 milliohms. So keep those numbers in mind. So again, there's 3 capacitors. You can see this one's set up as a shunt. This one is set up as a shunt through. And this one is set up in series. Again, all 3 of these are the same component. We'll just select the shunt through. And now if we move our cursor down into the valley here, we can see that we are at roughly 250 megahertz or so. So about in this area right here, and you can see this should be just around maybe 28 or so milliohms, and we are getting roughly, what are we saying, 30 milliohms or so. So it looks like about 2 milliohms, maybe 2 to 5 milliohm discrepancy between our measurement with the Nano and what the predictions are. So I guess the question is, can we trust this measurement? So one thing we could do is we could place 2 of these capacitors in series, and we're expecting that ESR to double. Again, 2 resistors in series, so I'm expecting this is going to read somewhere around 63 or so milliohms. And you can see, sure enough, we're reading 67 milliohms. You can see it's also changed our resonant point. Now this software, the way this works is that ESR measurement isn't based on the location of the cursor. It's actually doing the calculation automatically based on the valley. Of course, we still don't know absolute what that value is. Again, this original one could have been 15 milliohms, for example, and we doubled it and got 30. So is it really 30 milliohms, or is this something different? So here we have 2 50 milliohm resistors that are attached in parallel. This should give us, of course, 25 milliohms. You can see we're reading, what, 23, 22 milliohms? Fairly close. Now normally if you're making measurements like this, you're probably not using the nano. This thing actually has quite a bit of noise, so if you wanted to try to measure something even lower than this, let's say down to a milliohm for example, you'd probably want more data, so you zoom into that resonant point and then you do some sort of a filter or averaging on that data to try to get a more precise measurement. So if you've been following my development of the software at all, what I've done is I've created a common set of software that I'm using for all of my network analyzers. So essentially there's two different unique pieces of software for each network analyzer. There's a top level piece of software which is essentially the user interface, and then there's a piece of interface software that tells that top level how to communicate with the hardware. The remaining software is identical for all of my network analyzers. If you look at my GitHub account, you can see at the top level we have Joe Q. Smith, and there's the NanoVNA software. You can see there's a README file, and you can see I'm supporting the original NanoVNA hardware as well as the V2 Plus and the V2 Plus 4. Now it's very possible that this software works with other flavors of firmware and other hardware. I really don't know. These are the only two that I have available. What I can tell you is when I decided to go ahead and release the software, I was trying to help out a person who was trying to measure crystals. My original software for the NanoVNA has a feature that allows you to characterize crystals automatically. When he started looking at my software, of course, he ran into problems, and as we started to look into it, of course, he was using different firmware than what I had tested my software with. And of course, I had ran into problems similar to that with early firmware, where essentially you end up with random glitches in the data stream. And unfortunately, it looks like those problems still have not been resolved with some of the later firmware. There's actually a member on the EEVBlog who had changed some of the firmware for the original Nano. I believe what they were doing is instead of using a fixed settling time, which is what I think the new stuff all does, I think he was using the flags internal to the components to determine when he could actually step to the next frequency. So once he had made that change, I had never had any more problems with the firmware. And as a matter of fact, up till the point when I decided to go ahead and release this software, I was still using that old firmware from roughly a year ago. So down here we can see I have different links to the videos that I've made about the Nanos. The second sentence is very important. If you're installing it for the first time, use the main release. And that's located off to the right here where it says latest. So if we go to latest, you can see there's a whole bunch of files in here. This is actually one file. The problem is GitHub doesn't allow me to just upload a single file, which is really what I'd like to do. And this contains the LabVIEW runtime engine as well as the VISA library. So what you want to do is install this first. So this actually does contain the LabVIEW software, but it's quite old compared to what we're working with today. You can see it's version 0.1. So again, what you want to do is select the branch for the VNA that you're using. So if you're working with the Nano, just select this, and here's the download file. You can see we're at version 7. What I'm demonstrating here is actually newer than this, and I hope to have this released sometime by the end of next week. If you're working with the V2 Plus, just select NanoVNA V2 Plus, and you can see we're at version 1.01. Again, older than what I've just been demonstrating. This is looking at the software for the original NanoVNA. You can see we're now at version 1.08. Let's go ahead and we'll select link, and then we can select sweep. Alright, let's try measuring these same capacitors. Again, like before, we just start out by applying a through, and you can see we're at roughly 0 dB. Again, keep in mind that the original Nano can only sweep about 101 data points unless we use segmented. Normally I don't use segmented unless I'm looking at a narrowband component. Let's just start out. This will be our two 50 milliohm resistors in parallel. Again, we're expecting this to read roughly 25 milliohms. Looks like we're in the ballpark, so 29, 26, there's a 23.8. Let's go ahead and insert our capacitor. Again, we're looking for roughly 28 or so milliohms, probably a little higher, 37, 38, 33. Again, a fair bit of noise. One thing you could probably do is zoom in on the area that you're trying to measure. Again, you may end up having to add some ferrite to the cables, or just getting a common mode choke. You might also end up having to add some attenuators to try to help with the match. This is a 100 milliohm resistor. It's just a single 100 instead of the 250s in parallel. And you can see we're reading, again, a little high. It's reading about 107 or so milliohms, 108. Fairly close, I'd say. Again, we're in the ballpark. So hopefully it gives you some confidence in the measurement. When I made the review for the NanoVNA Plus, I mentioned that it couldn't be used for narrowband measurements. And again, that was the whole reason that I released the software for the original NanoVNA, because this unit is capable of making those measurements. So here again, we have our small fixture. This is nothing more than two 3dB attenuators and then two transformers. Again, this is here just for impedance matching. Again, if you're going to try to use a fixture like this, it's probably not going to work very well. What I've done is I've actually compared this original Nano against my other network analyzers, and using the same fixture, and I've also used my RLC meters. I also made a pole fixture, which is basically nothing more than an oscillator, and all those measurements compared fairly close. So what I'd like to do is just kind of walk you through how to take those measurements. Again, you're going to have to start out by building some sort of a test fixture. If you look in the manual for the software that I've written, I've documented this particular fixture. I would suggest that you build something like it. This one is good for taking measurements up to, I don't know, 25 megahertz crystals or so. You probably don't want to go much higher than that. Again, we just insert this fixture between port 1 and port 2. Again, looking at our software, you can see the center is set for the default frequency at 10 megahertz with a 2 megahertz span. Let's go ahead and insert this crystal. This one is 10 megahertz, made by NIMP. And you can see there's a definite peak, and it's right at 10 megahertz. So let's go ahead and zoom in. We do that by selecting the zoom. You can see zoom peak for narrowband crystal measurements. Again, it takes a fair amount of time to run through this. Unfortunately, the communications with the Nano isn't really all that fast, so wait for the button to pop back out. In the end, it zooms in with a span of 500 hertz. So it's just finished up. Let's turn off our reference. You can see we're at minus 19 dB down. Now I can tell you that's not correct. So this unit has to be calibrated, and again, the way we're going to do that is to apply a short in place of the crystal. We'll store that as our reference point, and let's go ahead and select our channel N-ref. And again, we can see we're at 0 dB, and let's go ahead and insert our crystal now, and it should be, yeah, minus 2 dB down or so, and that would be normal for this particular crystal. So that's actually one of the measurements that the software is going to be making. Let's go ahead and we can select Advanced, and you can see we're on our crystal measurement screen. If I right click on the center graph, we can select Clear Chart. On the left, you can see this is our series frequency. It's actually doing a fit, and it's looking at the peak as being roughly 9.996084 megahertz. And again, we can see if I touch this crystal, it drifts quite a bit. That's just the temperature effects of my hand. And you can see it'll take a little while for it to recover. What this is different capacitors ranging between 1 picofarad and about 100 picofarads. What we can do is insert these just as a sanity check. So let's just start by inserting our 10 picofarad capacitor. And again, we just select C0 cap. It'll take a little while for this to run, and you can see the frequency changes. It's doing all these tests at, I believe, 500 kilohertz is where I've got it set to right now. The idea is that we don't want to be anywhere near the resonant point of the crystal when we take that measurement, and you can see it measures 10.007 picofarad. That's just by chance. It's not normally going to read that tight. So now let's insert our crystal again. Again, we'll select C0 cap. And you can see this particular part measures roughly 5.3 3.7 or so, 3.8 picofarads. And again, let's just go ahead and clear the chart. Now really what you want to do is let this thing settle. If you're going to be running a fair number of these crystals, I'd recommend that you insert them using tweezers rather than your fingers. Again, the idea is that, you know, as you hold on to these, you're heating them up, and it just takes a fairly long time for them to settle. Again, as long as you're running a lot of, let's say, 10 megahertz parts, there's no need to calibrate the unit between each measurement. So all you need to do is just insert the new part, measure C0, and then wait for it to become stable. And see, starting on the upper left, this is the series frequency in kilohertz, and we have the bandwidth in hertz. This is the attenuation. Again, you remember when we were looking at the main screen, we're down about negative 2.1 dB or so. That's this number here. The loss resistance in ohms, this is the Q, so roughly 11,000. Loaded Q, 22,000. The inductance in millihenries, 11.6, and the crystal capacitance is, it looks like, about 21.8 femtofarads. What you can do then is add a serial number, a brand, and a model, and we can save this to a data file. And then what we can do is select crystal sort, and we can use this to sort through the crystals that we've collected data for, and we can select the number of poles for the crystal filter that we want to construct. We just have it set for 4. We can change this to whatever, 5-pole filter. Select crystal sort. Next we want to give it a file name, so we're just going to go to crystals, and this is some data for crystals that I've looked at, and this highlights the crystals that we would want to use out of this lot. So it looks like for this crystal filter we want to use 10, 2, 11, 6, and 9. In the upper left, these are the values for the 5 crystals that we've selected. I have built a couple of different crystal filters that I've shown. This particular NanoVNA does a decent job making the measurements of the actual filters once it's been built. Well, I think that's going to be it for this video. Hopefully it gives you some idea what the new features are with the software. Again, I hope to have that released sometime this week. I still have to update the manual for it and spend a little bit more time testing the software, but you know, hopefully fairly soon. So that's all for now. Stay safe until the next video. We'll see you then.